Well, thank you all for coming. And if my remote doesn't work, then Kathleen, your job is to hit the page down button when I point at you. But I think it's going to work today. Okay, some interesting things about me. Let's see. I'm not from Iowa, but I went to school there for 10 years, and that's longer than I lived anywhere else. So I tell people I'm an Iowan. I studied inorganic chemistry, which for most people who remember chemistry, that's the boring math part. You did it first, before you did the interesting organic stuff. But after you get through the interesting organic stuff, you get to the interesting math part, which is the other elements, those other 100 elements, not carbon. So it's worth it to go all the way through and take the upper level courses, because that's where the really cool stuff is. Those of you who finish chemistry and go on to be doctors, you don't get to do that. So what I'm going to talk about today is the research that I did with two different sets of students in 2 consecutive summers here in Grand Rapids. 2 summers ago, in 2005, I had senior chemistry majors Melissa Conklin and Megan Broderick working with me, and then this past summer I had Rob Sturm and Leanne Griffiths doing work with me. And so this is mostly their work, not so much stuff that I did, because I was just the advisor/supervisor. Anyway, we looked at some environmental chemistry the first year in the water and the second year in the soil around West Michigan. It works. The first thing I'd like to tell you about a little bit, though, is why we do research anyway at an undergraduate liberal arts college like Aquinas. This is a philosophical statement or explanation. Why do we even bother? Because we're a small school, we don't have a lot of resources. I'm probably not going to be able to do the kind of research that gets into the highest quality journals, just because we don't have enough time to do that kind of research. And many faculty who come to work at a school like this aren't really interested in that sort of lifestyle. And so why do we even bother doing the research that we do is a very interesting question. One of the reasons, and the reason that I do it, is because I think it's a valuable experience for the student, more so than for me. It's great for me. It's interesting. It's my field. It's what I like to do on weekends. But for the student who might never have done any kind of research before, it's an eye-opener. If you're just going to college taking classes, you might get the idea that chemistry is all about working math problems and looking up the answer in the back of the book. And that's not what chemistry is. That is so far away from real chemistry that you can't even imagine what real chemistry is like if that's all you've done. And so the reason that I think research with you guys, research with undergraduate students is so important, whatever the field, is because that's what real chemistry is. It's doing the research. It's playing with chemicals. It's going into the lab every day as if it were your job and finding out things. So that's the purpose, in my mind, of what I do. And that's why I try to find as many opportunities as I can for my students to experience research, even if it gets me nothing. As I said before, though, at a small place like this, we don't have as many resources available to us as a big university would have. We might not have the cutting-edge everything. We might not have thousands of dollars that I can devote to your project. We may not be able to fly all over the country and take samples from the ocean and the mountains and stuff. We might be limited to nearby places. And we also don't have a lot of time. My schedule during the academic year, I'm sure like yours, is really full. And so no research happens during the academic year if it's up to me. It has to wait until the summertime, or it gets stuck into some little corners between classes, or when I have a spare 15 minutes to give to you. So one of the restrictions is that we can really only do chemistry research from May until August, and we have to do it all between May and August, because we won't get another chance until the next May. So that's hard. You'd like it to keep going all the time, but we just can't. One of the ways that my research has been helped is by getting involved with the Pierce Cedar Creek Institute, which is near Hastings, Michigan. It's south of here, about an hour's drive, in the middle of nothing. But it's a very nice, very beautiful kind of nature-centery place. And 2 years ago, they decided that they'd like to get into the undergraduate research area. And they started offering these URGE grants, which stand for Undergraduate Research Grants for the Environment, something like that. And they offered stipends for students and faculty, as well as a small supply budget for teams of people who could go to their institute and do some kind of work, some sort of research, basically anything. It was open to any field. They are predominantly biological and ecological, but then there's me. And the first year I did this, there was also a geographer, I think, who did some studies there. And so it hasn't always been all biologists and me, but mostly biologists. And so about 2 years ago, I recruited 2 students by standing up in class one day and saying, who'd like to do some research with me? I got 2, we wrote a grant, and that was our first Pierce Cedar Creek project. The summer of 2005, here we are. The title of our project was Water Chemistry of Brewster Lake. These are the 3 of us. This is Megan Broderick. This is Melissa Conklin. And then me, of course. Melissa has since graduated from Aquinas, one of our best students, and she works now full-time as a research scientist at Alticor over in Ada. Megan is finishing up a French major, and she'll be graduating this spring after she goes to France. So good for them. This is a picture of Brewster Lake, which is a small lake on the property of Pierce Cedar Creek Institute. This picture was taken, it looks like late spring, early summer, very nice looking. I didn't take the picture, so I'm not sure. It's a small lake, about 10 to 15 acres is all. It's not very deep. It was formed by glaciers, which I guess dug out the landscape there and then was filled in with water later. And the land surrounding the lake, as well as the lake itself, have been protected from human activity for at least the last 50 years. The person who owned this property didn't allow boating, fishing, swimming, trespassing, hunting, or any other use of his property going back 50 years or more. And so he wanted it to be protected, and the Pierce Cedar Creek Institute got this land afterward, and they're protecting it now under Michigan easement, I guess. The purpose of our work 2 summers ago was to measure the health of the lake water and to determine the trends in several properties throughout the summer. So we had a 10-week study, and we measured certain properties of the water, 7 of them, each week for 9 weeks, to see what the trends were in each of those properties and to get an overall picture of whether the lake water itself was healthy, whether this was a healthy lake. The 7 chemical and physical properties that we measured were water temperature, pH, the amount of dissolved oxygen, the concentration of nitrates, the concentration of phosphates, the alkalinity, and the conductivity of the water. And some of those things are related to each other. We were going to take 10 weekly measurements, but it turned out we needed the whole first week to prepare, so we ended up with only 9 weekly measurements. But we took samples around the perimeter of the lake, and we had stakes on the edges of the lake with marking tape so that we could go back to the same location all the time. There turned out to be 22 of these sites around the perimeter of the lake, roughly 30 meters apart. As summer went on, the vegetation grew up where there was none in May, and so the perimeter of the lake got harder and harder to get to. The shore of this lake is not a distinct boundary. There's no solid ground with water on one side and dirt on the other side, and it got closer to the center of the lake as vegetation grew up on the shoreline. So after the first couple of weeks, we sort of weren't on the shore anymore. We had to kind of guess how close we could get to those original stakes. So it sort of moved in. This is an aerial photo of the property with our sampling sites marked here. These little green circles around the perimeter of the lake are where we took our samples. This one marked boats is at the location of the boat launch. We had to take a boat to do these samples, and so we'd get a little rowboat and toss it in the lake and then row all the way around the lake taking samples. It would take about 2 hours each time. We also took some samples here. 1B and 2B refer to sample sites on the creek that comes out of the lake. And I'm not going to talk about those samples today, but we did measure the same properties for about 6 weeks at each of those locations to kind of compare with the lake water itself. This area here and this area here are wetlands, and so that gives you kind of an idea of what's surrounding the lake. Back here is more dry agricultural field and forest in this area. This is the Pierce Cedar Creek sort of parking area, visitor center, and main campus. So there's some buildings there. And then this building is the wet lab where we did some of our research work on the property. It's kind of a barn with scientific bench space and running water. Oh, this is a road, by the way. This here is the dirt kind of gravel road that runs right through the middle of the property. Here are some pictures of the students. I'm the photographer, so I'm not in any of the pictures. But these are the students doing some work. Here we are. I think this is Melissa taking a sample on the creek. This is the two of them. They're doing two different measurements right here. Each of them has her own instrument, and they're taking measurements of Megan here is doing phosphates, and Melissa is doing nitrates. Here we have Megan titrating. She liked titrating. And this is Melissa pipetting her samples. So to give you an idea of the types of things we did, all of these tests shown here are in Aquinas' laboratories. So after we took the samples, we could take some measurements right there on the property, but for everything else, we had to drive the samples back to Aquinas and then analyze them here. So we did quite a bit of work here in the evenings after doing some work down there. The summary of what we found, most of this is not a surprise. If we start in May and we measure each week until the end of July, the water temperature increased. Yeah. We started at an average temperature of 18 degrees the first week, and by the last week we had an average temperature of 30 degrees. That's of the 22 samples. And here it is in graphic form. Week 1 way over there on the left, week 9 here on the right. Something happened in week 5. It was cloudy that day or something. I don't remember. Maybe it rained. But generally, there was an abrupt increase in the first few weeks, and then it sort of stabilized. And then our study ended, so we didn't get to see the end of summer fall decrease in temperature that we would expect to see. Secondly, the dissolved oxygen amount. The amount of oxygen dissolved in the water decreased from 9.5 milligrams per liter to only 5.5 milligrams per liter during the same time period. And this is our graph of that. Partially because the water temperature is increasing, and probably also because there's more life in the water in July than there is in early May. Think of all the plants that sprung up. Think of the small creatures, the fish, other things that live in the lake and are using that oxygen. So that can change over time as well, but probably the temperature has a lot to do with it. Thirdly, the pH of the lake didn't really change at all. This shouldn't be a surprise. Lakes should be buffered quite well, so we shouldn't see much change. It was between 8 and 8.5 pH units throughout the summer. It went up and down quite a bit, as you can see here, but pretty much the same all the time. Alkalinity, which is the amount of base or the amount of calcium carbonate present in the water, is related to pH. It's sort of part of that buffering system. And we found that over the 9 weeks, there was a slight downward trend in the amount of alkalinity in the water. It went from 190 down to 160 parts per million as calcium carbonate. And so this is what the graph looks like of that. Again, I think this is what we should expect. Conductivity, which measures the amount of the amount of dissolved particles in the water. It's measuring how much current you can pass through amount of water, and that pure water would have a very low conductivity, would not conduct water very much, but something with a lot of ions dissolved in it should conduct electricity very well. And it decreased a little bit from 360 to 260 micromos per centimeter. And here it is in graphic form. We really like the unit of this, micromos. We thought that was great, and we could never spell it correctly. Then these last two, which were the ones we ended up concentrating on the most. Nitrate concentration tended to be the same every week. It was around 17 parts per million the way that we measured it. This is really high for nitrates in a lake. But you can see here that it was, especially these last few weeks, quite constant over time. But always quite high. I think that the EPA recommends or states that anything more than 10 parts per million is a problem, and we were measuring almost twice that, and we weren't sure why that would be, since this was a very protected lake with not very much in the way of nitrates being input. We couldn't find a source of high nitrates in the area because there wasn't a lot of agriculture, there wasn't a lot of human activity, which is generally why there's high nitrates. And so what we ended up doing was concluding that there might be a problem with our method, or something in the way that we were measuring this. I'm going to come back to this in a second, I think. Phosphates, on the other hand, had the opposite problem. We actually could not measure any phosphates in the water. It was below the detection limit, and for a long time we were thinking that we just weren't doing it correctly, that we weren't performing the test properly, and so we kept getting, actually we were getting negative numbers for concentration. It doesn't make any sense to have negative concentrations. And so eventually we decided that it wasn't us. It was the fact that there is very little phosphates in this lake. There shouldn't be much phosphate in the lake. Aside from what is naturally dissolved from rocks and other sources, phosphates generally come from things like soaps and detergents that are flushed into the waterways. And this lake has no inlet. There's no river flowing into it. It only has an outlet. I think the spring is at the bottom or something. And so without any human activity, without any sewage or effluent going into the lake, maybe there aren't that many phosphates. And our method was only good down to, I want to say 0.5 parts per million anyway, which is a very small amount. So we just weren't able to detect the tiny, minuscule amount of phosphates that was probably in the water from natural sources. And so we didn't find any, but we thought it was us for a long time. We thought we just couldn't do it. And we were able to conclude at the end of the summer that Brewster Lake is quite healthy. We didn't find any pollution of the types we were looking for. And that was exactly what we thought it would be. So this wasn't earth-shattering news here. We did, however, elucidate the trends in each property during those 10 weeks, or at least the 9 weeks that we measured them. We could see what changed and how fast it changed, which was something that no one had ever done for this particular lake. And so this provided valuable information for Pierce Cedar Creek and for future work in the area. As I mentioned, only the nitrate concentrations really bothered us. After we figured out what our problem was in measuring phosphates, only the nitrates remained an issue because they really shouldn't be that high. And so what happened after this 2005 summer, both Melissa and Megan were seniors here at Aquinas, and as chemistry majors they were required to do a year-long independent research project. And so they decided that they would continue this work. Megan looked at lead concentrations in a variety of lakes, including Brewster Lake in West Michigan. And Melissa continued measuring nitrates. She picked out 2 other lakes to compare, one that was surrounded by agricultural fields and one that was surrounded by residential homes. And she measured nitrate concentrations using a different method that was more precise, more carefully controlled, as well as taking new samples from Brewster Lake and compared the 3 lakes, and she decided after that that the real levels in Brewster Lake were also extremely small, on the order of 1 part per million. The reason that our first analysis gave us such high levels was because our method did not correct for any dissolved organics in the water. And so all we were doing was we were measuring everything that absorbed at a certain wavelength. And it turns out that although nitrates absorb at that wavelength, so does every other organic compound. So if there was any sugars or proteins or wood bits or parts of fish or anything in the water, all that stuff would have a chance of absorbing and giving us an erroneously high value for nitrates, because we were making a wrong assumption that everything we measured was nitrates when it really wasn't. So using another method, which I'm not going to go into because that's really her work and has nothing to do with me, she found that Brewster Lake had very low levels of nitrates in reality, less than 1 part per million. She also found that the residential lake was slightly higher but also low, and the agricultural lake had the highest levels, but they were still quite low. I think she found under 10 parts per million there. Most of that, we believe, comes from the application of fertilizer to the fields that would then run off into the lakes. Ah, yes, this is what I said. The 2 students went with me to a regional American Chemical Society conference last May, which happened to be held in Frankenmuth. And so the 3 of us went to the exotic city of Frankenmuth for 2 days, and we presented this work as a poster. They presented, I hung out. And they did an excellent job and had a really good experience being at a professional conference. The other presenters in the poster session were not all students. There were some students presenting, but many of them were professors or graduate students or industry people. So they were measuring up against regular old chemists. And so they were also regular chemists. And I was very proud of them. If you'd like to see their poster, that's hanging on the wall on the 2nd floor of Albertus Hall, just outside my office. They did a really good job, and they had a great experience with that helped them go on to get, well, in Melissa's case anyway, go on to get a job. And we hope it will have the same effect for Megan. Moving on to the following summer. It's a repeat of the first summer as far as I asked for volunteers to help me do some research. We wrote this terrific grant proposal. It was funded, and so last summer, another 2 students and I worked on a project which dealt with metal concentrations in the soil. This is me and the 2 students at the beginning of the project. This is Rob Sturm, who's sitting back there, and this is Leanne Griffiths, who is tutoring, so she can't be here today. These 2 students and I collaborated on the grant proposal, and they did most of the work while I got to wash dishes. Here are some terrific photos, again, without me in them. Here, we're going to talk about this in a few minutes, is the little marked stakes that we used to make sure that we were taking our samples in a predictable pattern that was reproducible every time. This is called our interior pattern. It looks sort of random from here, but it's actually several different lines, parallel lines of samples being taken. There's 10 total. And here, these stakes, this happens to be along Fulton Road, just out front here of campus. This is the roadside sample pattern, which has 7 in a row just along the edge of the road, and then in the middle there are 4 going directly away from the road at 1-meter intervals. The purpose of this study was to measure the amounts of lead, copper, and zinc metals in various types of soil, mainly on the property of Pierce Cedar Creek Institute. But we also wanted to find out what the impact of human vehicle traffic is on those 3 metals concentrations. And so we took some samples here in Grand Rapids for comparison. This one, as I said, is on Fulton. We had another set of samples that we took along the East Beltline out here by, kind of by Cascade Road on that intersection. The location of the samples on the Pierce Cedar Creek property, this is an outline map of the property. Here's the lake again, so you're looking down on it the same as you were in the previous aerial view. The different colors on this map represent different types of soils. And then here is the visitor center parking lot complex. You can see that there's a lot of land here. It's about 660 acres worth of land, so it's quite a lot. We took 3 sets of samples along Cloverdale Road, which was, as I told you before, this road that cuts through the middle of the property. You can see here's this yellow splotch stands for Thetford type soil. So we took 1 sample there, 1 sample here in a Marlette type soil, and 1 sample here in Parrington soil. And then we tried to find a matching soil type somewhere that was far enough away from the road that we could assume no road effects. And so we have an interior sample here. That was the one in the photograph I showed you that had all the green grass. We had a marlet one way back here in the forest, and we also had a Thetford here. And then we took a second marlet on the other side of the road also. So we had these 7 Pierce Cedar Creek locations. And we hoped to be able to compare the roadside concentrations of metal with the interior concentrations of metal in order to find out if traffic on the road had any effect on the amounts of metal that was getting into the soil there at Pierce Cedar Creek. Here we have the pictures of the students working. Again, I'm not in any of them. Here's Leanne taking a sample with this soil corer. I think that same location with the grass out in the middle of the field. And then again, just like the previous summer, we couldn't do most of the analysis on the property at Pierce Cedar Creek, so we would bring our samples back here in little plastic baggies and do most of the analysis here in the chemistry lab. So here we have Rob and Leanne crushing up the soil in preparation for some analyses. This one is Rob testing the pH of the soil. And here we have, this one's a little bit dark, Rob and Leanne analyzing metals. We used atomic absorption spectroscopy, and so this is the instrument that we use to measure the concentrations or measure the absorbance, which translates into concentration. So we had a good time. We worked again about 11 weeks last summer on this project. It took us a week or so to get it all set up and get started, and after that we did 1 or 2 sets of soil samples every week. And a set was the 10 bits of soil that we dug up in a specific location. So if you remember back to the pattern of stakes with red tape on them, there were 10 of those at each location, and we had 7 locations down at PCCI, plus, well, we did 3 up here. So there were quite a few that we had to get through. What we found, in summary, was what we expected was true for lead and copper, that the concentrations of those 2 metals was higher near the road. But for zinc, it was not. So this is a graph showing the amount of lead, here's lead concentration on the y-axis, versus the different types of soil. And then the roadside samples are here in the dotted bars, and the interior, the non-road samples, are here in the white bars. And for lead, if you ignore this one here, all of the roadside are higher than the corresponding interior. And so it seems like near the road there would be more lead in the soil than away from the road. Okay, there is this one exception, and we can't really explain the one exception because it was totally different, not only from its own road, corresponding road site, but also from the other interior site of the same type soil. We think, however, that it might have something to do with the fact that this soil sample was taken near the wet lab. Is that the one? No. It was just in the middle of the roads. So we don't know why that is. Unfortunately, we can't explain this one. But it is the only exception. So all the other ones followed the expected trend. This is the same kind of graph for copper, and the same thing is true here, that the roadside samples for each type of soil have more copper than the interior. So we have much less copper, it looks like, the farther you go away from the road, perhaps, or at least when you're not right on the road, you have less copper. Zinc, however, was the opposite. And this is the same type of graph showing zinc. Zinc near the road was very low. Zinc away from the road was quite high. We're not sure about this, except that it doesn't seem to be that zinc depends on any kind of vehicle emissions or vehicle exhaust, the way that copper and lead can be attributed to parts falling off of your car or exhaust from your car carrying metals with it. It doesn't seem that zinc has its origins in those types of emissions. So it doesn't look like zinc is connected to traffic. We found that the metal concentrations were always larger when we took samples near more highly traveled roads. So, for example, taking a sample near Fulton Road resulted in higher concentrations of all the metals than taking a sample out in the middle of the woods. I don't know about you, but I'm not too surprised by that. Well, I have no graph there, but this is a graph of just what I said, that if you compare the amount of lead, copper, or zinc that is in the soil near, let's say, Fulton Road or the East Beltline or something like that, compare that to any of the sites down at PCCI, the sites near the heavily traveled roads have more metals in them. If we also compare the amount of metals in soils near a road like Fulton Road or the East Beltline, if we compare that to samples taken near Cloverdale Road, that little gravel road on the property down there, the more highly traveled roads here in Grand Rapids have more metals than that road does. So whether you compare all the PCCI samples near the road or interior to the highly traveled roads, or if you compare the less traveled road to the high traveled road, it's still true that more traffic appears to result in more metals in the soil. This last question, oh, there's one. This is lead concentration. I think this is the graph I was trying to show you before. This is lead concentration. These are the highly traveled roads, Fulton, East Beltline, and all the PCCI samples. Yeah, East Beltline is the purple wavy one. And this is Fulton. And while it looks like the East Beltline has much less lead in it than the Fulton samples do, we think that the reason for that is because on the East Beltline there's that paved shoulder part. It's almost 2 meters wide. It's like a little driveway on the side of the road. And so we weren't able to take samples right on the road surface the way we were at Fulton. If you go out to Fulton, there's a sidewalk, there's a little bit of grass, and then there's the road. And so we can get right up close to the road and take our samples. But on the East Beltline, we were far away from the actual surface, and there's like a gutter in the side that would trap anything rolling off the road into there. So it looks like East Beltline is quite low. It's still higher, though, than the PCCI samples. So that part's still true. But Fulton was definitely our big winner here as far as lead. OK, so that's what I was trying to show you before. So the one that didn't show up must be this one. No, it's still this one. This is showing us distance from the road. So our number 4 site was right on the road surface. And then these were each 1 meter away from the road. So this site was 1 meter from the road surface. This was 2 meters from the road surface. This was 3 meters from the road surface. And you can see that, especially in the Fulton Road samples, that the trend is for the amount of lead in the soil to decrease the farther you get away from the road. And that supports our argument that the vehicle traffic on the road is what's causing this lead to get into the soil. Because as you go farther away, there's less of it. So perhaps that would explain. Also, East Beltline has the similar trend. As you go farther away, there's less lead in the soil. And we found this to be generally true. At PCCI, it's not. It doesn't appear that those bars show a trend decreasing concentration as you go farther away from the road. Okay, I thought I had another graph, but I guess I don't. Maybe I do later on. So in conclusion about this summer's study, we found that at the property, at Pierce Cedar Creek, no matter where you test, the concentrations of those 3 metals are quite low. They're much, much lower than any of the samples we took up here in Grand Rapids. We took one set of samples out here on the campus under the trees, and even those were very high in lead, copper, and zinc compared to the Pierce Cedar Creek samples. In urban areas, that is, of the samples we took in Grand Rapids, either near the road or not near the road, those concentrations were quite high. And if people were out eating dirt, it would be a problem, because that would be a lot of lead to be in your system. But since people generally don't eat dirt, it may not be as big of a problem as it sounds like. To say 140 parts per million of lead is kind of scary sounding, but you're not eating the dirt, so it's probably not going to affect you very much. You're not going to be ingesting that, and it's not going to get into your system at that high of a concentration. I'm not saying it's not to worry about, because we would prefer not to have lead in the soil. Question?
This may be a silly question because I am not a chemistry major, but if plants were grown in soil that was high in lead content, would eating those plants be harmful to you?
some plants will absorb metals from the soil and could then, if you eat the plant, could introduce metals into you. But not all plants will absorb the metals, and not all plants will absorb all metals equally. So it kind of depends on what type of plant, and even then, how much of that plant you're eating. So for example, I have a garden at my house, and while I was doing this study, I was growing vegetables in my garden, and I was thinking, oh my gosh, if all this metal is getting into my tomatoes, and then I'm going to eat these tomatoes. But probably the amount that happens that gets through the plant and then you eat it is probably small in most cases. There are probably exceptions to that, but in most cases I wouldn't worry about it.
Could you test for that then? So
You
if
could.
there's a follow-up,
You
let's say
could.
Theoretically, you could grow a garden in these areas, and then actually once the tomatoes grow, you can test and see what the levels were and do it once.
Yes.
And
That would be an excellent test to do, to grow certain types of plants in soil that you knew had a certain amount of lead, let's say, and then to test the plants for lead later to see how much lead they had absorbed. If you grow the plants from seed, then all of the lead would have come from their environment when they grew. So yeah, that would be an excellent thing to try. Ma'am.
So, how did you guys sleep out at Pierce Creek? Or I know you came back here to do the testing, but did you stay out there and then come back here, or did you stay here and go out there?
We stayed here. Leanne was also doing an internship out at Alticor last summer, and so she would work at Alticor from 7 in the morning until 4, and then she'd do her run, because she's also a runner. She runs cross country and track. Then she'd run or bike back to Grand Rapids, meet us at the lab, and then we would work for about 4 or 5 hours into the night. So we worked until 8 or 9 o'clock most nights. Rob also had to work, so he would work during the day and then meet us there. I was working during the day, so we weren't able to stay the night down at Pierce Cedar Creek because we all had.
Down once a week to get your samples?
We did. We tried to all go down together, like on a Sunday, collect the samples together, bring the samples back up. They had to be in an oven to dry out overnight anyway. So if we collected them Sunday, then we could start the analysis Monday night after everybody got done with work.
Because I know there is dorm space down there, right?
Yes, they do have living space, and they really want students to live down there and get the full experience of being in a crowd of people all engaged in scientific inquiry together. All the other groups, I think, spent at least some of their time living on the property. Some of them only lived down there the first 2 weeks of the summer, and then we never saw them again the whole experience. Other people spent their entire summers living down there and only came home on weekends, especially the people who came from far away, because there were students there working there from Central Michigan University, from Albion, from Kalamazoo College, from Western Michigan, from all over Michigan. And so some of them had a much longer drive than we did, and for them the balance of spending time down there versus not was much more in the favor of living down there they have a farmhouse, and so all the kids could live together. And they provided meals. Was there another question?
Well, do you assume the source of the metals is exhaust?
Well, that would be one possible source, the exhaust from cars and trucks. But we don't expect there to be much lead in those exhaust fumes anymore now that leaded gasoline has been phased out. So although there might be some residual lead in the soil left over from the time before leaded gasoline was phased out in the 70s, perhaps a larger source of lead comes from the wheel weights, lead wheel weights, and they tend to fall out of the wheels, apparently, and the little wheel weights roll around on the ground. They get crushed by cars and ground into a powder on the roadway, and then it gets washed into the shoulders of the road. So that and other components of the car that wear away, like copper, might come from brake parts that get worn away as you brake, and so the small shavings of those parts fall onto the road, get ground up, and eventually are washed into the soil at the side of the road. Things like that. We weren't really able to find a good vehicular source of zinc, which is why I said what I said about zinc earlier. But for lead and for copper, it does appear that cars and trucks, well, not exactly the exhaust, but other parts of those vehicles might be mostly to blame, which is something that we didn't think of when we started the study. Sir?
I had heard that car tires they leave residual lead. Is that accurate?
It may be. I don't know about tires. It may be. I know that there's more than rubber that goes into the tires, so it could be. Rob, do you know about tires?
Yeah, there's some lead and a little bit, but that was going to be the main source of zinc was tire wear.
Okay. Okay, so to sum up, Rob is now a senior, and so Rob has to do his required senior research project, but he decided that he didn't want to continue working on this same project, which is fine. And so instead, he's going to be looking at certain antioxidant compounds in red wines for his senior research project. And we are looking forward to seeing that. Leanne is only a junior this year, so she will not be doing her senior research project until next academic year. And so, of course, we have no idea what she'll plan to do with that. We are hoping, the three of us, to again present the work as a poster at the next regional ACS meeting, which will be in May, I think in Cincinnati this time. The other option would be the national ACS meeting in March, but since that one is during a school week, it may be more difficult for us to go down just for a poster session. Even though it's in Chicago, it may be difficult for us to get to the undergraduate poster sessions there, and much more easy for us to go to Cincinnati in May. We'll see how it goes. So in the end here, I need to acknowledge most of the work, as I said, was done by the 4 students. I do something, but it's certainly not as much as they do. They worked very hard both summers. They put in a lot of hours. They did a lot of research outside of the lab and a lot of thinking outside of the lab, and so they are to be commended for doing all of this work. I couldn't be here talking about it if it wasn't for them all doing excellent work. So here are the 4 students. I have to thank Pierce Cedar Creek Institute, of course, for giving us the opportunity. They did pay us stipends, so they did provide a little bit of money for us, as well as buying most of the supplies that we needed. The Aquinas Chemistry Department provided all of the space for us to work here. They provided my time, I guess, and all the other chemicals and things that we didn't buy were provided by the department, in addition to all the instruments and overhead. And then I need to thank the dean's office here for paying for the 2 students and I to go to the ACS meeting last May. That money was provided by Glenn Barkin for us to travel over to Frankenmuth and to stay in a hotel for a night, which was definitely worthwhile. And so I think that's the end, and if there are any other questions, I'd be very happy to answer them or to talk to you more about this or other research.